So welcome everybody to the last talk of today. I know I'm between you and the beer, so I'm not trying to make it overly long tonight. Okay, so this talk is called Integration and Conversation Patterns for Microservices. And this is all about how to build systems that you can scale, evolve, and operate individually. And I believe that should be interesting for everybody. So in my experience as software architect, there are two things that are really essential when it comes to designing systems. One is divide and conquer, and the other one is loose coupling. And when you deal with microservices, you already apply divide and conquer. And a good way to reach loose coupling is asynchronous messaging. Now, when we speak with our customers about designing the communications infrastructure for their microservices landscape, we often hear that they have REST APIs on their radar, but not necessarily asynchronous messaging. And we think that messaging can have a number of advantages in certain scenarios, definitely not in all of them. And this is why the basis of this talk deals with integration patterns that are based on asynchronous messaging. However, messaging is obviously not the solution for everything. In the end, also in architecture, it's all about using the right tool for any given job. And that means that for some integration problems, there are definitely also other solutions that are better, like all kinds of APIs or streams or buses. Okay, but because of what I have just said about our customers and integration scenarios for microservices, often thinking about REST, this is the context for this talk. However, the patterns that I'm showing are of universal use. They are not bound to the context of microservices, but they are valuable for all kinds of architectures. And this is why this talk could also be called Integration and Conversation Patterns, not only for microservices. But let's have a quick look at the agenda now. So I'm going to spend a few more words on the motivation for all this. Then I'm going to introduce you to a number of fundamental integration patterns, most of them based on asynchronous messaging. And then to make this more tangible and to put some flesh to the bone, I will also introduce you to some real world use cases so that it really becomes quite illustrative. Okay, a few more words on the motivation side, and I can actually cut it quite short with a quotation from one of my previous colleagues, Tim Bray, nowadays a general purpose internet software geek. And what he said is, if your application is cloud native, large scale or distributed, and doesn't include a messaging component, that's probably a bug. And I believe Tim is absolutely right with that. But why is that so? So synchronous systems come with some inherent drawbacks. And one aspect is that they are by nature tightly coupled, at least during runtime. If you imagine, there's a synchronous call from one system to the other that naturally blocks resources on the calling system. And if you think about a larger landscape of microservices, when a request comes in from the outside, that might lead to a longer path inside that landscape. And that means that in every service on the way of that path, resources are bound while the last item or the last service in the chain is processing the request. And all those downstream dependencies now can really easily have an impact on the upstream callers if they are out of resources, if they are buggy, if they return nonsense or so. Particularly when upstream callers then also bombard downstream systems with retries and so on, that can easily amplify. And that's why we have mitigation patterns like circuit breaker in the first place. But besides of that pure nature, there are obviously also some things that take too much time to wait, which we'll also see in one or two of our use cases, or some things are simply asynchronous by nature. So it's always worth to take a look into this. All right, now let's have a look at the integration patterns I brought today. Patterns are in principle always a great idea. They provide a lingua franca for architects, also for developers. So everybody knows what the other is talking about. And if you deal with software development, for instance, you probably know the Gang of Four patterns catalog. And when it comes to integration questions, there's also a pattern catalog that I would consider a standard one. And that was published in a book called Enterprise Integration Patterns, which was authored by Gregor Hope and Bobby Wolf. I'm sharing the website for the book where you can simply also read about all those patterns. You can use the QR code here to quickly access it. And if you have read that book or have browsed through that pattern catalog before, some of the patterns will probably sound familiar to you today. I want to start with the very beginning, and this is about message exchange. And we can distinguish here between one-way and request-response messaging. So one-way messaging, as the name suggests, there's a sender, there's a receiver, and there's that message channel thingy in the middle. And that immediately shows how that message channel decouples sender and receiver from each other. So they don't need to know anything about it, and they actually shouldn't know anything, or at least not too much about each other. And as I said, in this case, there's no response expected. Sender sends message A to the channel, then all good. And the receiver will eventually receive message A from the channel. The request response scenario is different. And now we also see a conversation here. So this can be seen as a conversation pattern. So we have the requester on the left-hand side that sends a message into the request channel, which is received by the responder. And now the responder works on the response and sends it back into the response channel. So far, so good. But this might raise some questions. So if you know that request response pattern, for instance, from HTTP-based activities, like in REST APIs or so, then it's synchronous, and it's quite clear where the responder needs to send the response to, because the connection is open. But here, how should the responder know where to send the response to? This is addressed by the return address pattern. So that's a piece of meta information that the requester adds to the message in message A, and the responder can extract it from there and then is asked to use that information to send the response back to the requester. Excuse me. Now, there's another question that might raise also for you. When the requester receives an incoming response, how can it know for what original request it was? So this is addressed by the correlation ID pattern. And again, that's a piece of excuse me, right at the right time. There's the coughing going on, I'm sorry. Okay, so the requester again adds some meta information to message A, which contains a unique correlation ID. And the responder again is asked to forward this correlation ID into the response. And now the requester can assign the incoming response to the previous request. After this is all clear, now we should finally have a look at those message channels that we have seen before. So in messaging, we can distinguish between point-to-point and publish-subscribe channels. And point-to-point channels are implemented by queues. Publish-subscribe channels are implemented by topics. And it's also called fan-out messaging. Let's have a look at the characteristics of a queue. So what we can see here, there is a sender on the left-hand side. And by the way, there can be multiple senders. It's just to make the diagram easier to read, I just put one here. And that applies to basically all the diagrams I have. In this example, the sender sends messages ABC into the queue. And what we can see on the right-hand side, we have a number of receivers, 3. And each of those receivers receives one of those messages. And that's one basic characteristic of queues. So every message is consumed by one receiver. And that directly brings us to a very nice characteristic of a queue, because by that, you can easily scale out on the consumer side. If there is so much traffic on the queue or so much messages waiting there, that the existing receivers that you have are in trouble processing them in time, sorry, you can simply add more compute resources on the receiver side to cope with it. On the other hand, you might want to cap also the amount of compute resources that you spend on the right-hand side. That can be for cost reasons. You don't want to scale out until your bank account breaks and so on. It can also have technical reasons. In this case, there's another nice characteristic that kicks in here because queues also buffer messages. And with that, they can flatten peak loads for you. So the queue buffers the peak loads that comes from all the senders, and the receivers on the right-hand side can consume those messages in their individual pace. Apparently, the amount of messages that can be buffered in the queue is dependent on the product you use, on the service you use, and so on. But in principle, it provides this characteristic. And with that, queues can also be called buffering load balancers because they balance the load on the receivers that are available on the right-hand side. Okay, let's have a look at topics now on the right-hand side. Now it's a bit different because as we can see here, and the parties are called publisher and subscriber here, because we have the pub sub pattern. Every subscriber on the right-hand side will consume every message that appears in the topic. This is like broadcasting something. If you turn on your radio, you will listen to the radio show. If you switch it off, you will not listen anymore. And the same applies to all your neighbors and everybody else who is in vicinity of the radio station. That means if that has a number of implications, actually. So the first one is, what if my subscriber, one individual subscriber process cannot cope with the load anymore? There's too much load coming in from the topic. Now, if we add another subscriber to share the load, this will not work because every subscriber, as we just have seen, will receive every message. I'm going to park this question or this problem for a minute, and we will come back to it later. Another thing that I just said, you switch on the radio, you listen to the show, you switch it off, you don't listen to it anymore. This applies more or less also to subscribers. If your subscriber is subscribed initially to the topic, they can receive the messages. If the subscriber goes offline for whatever reason, a bug, for maintenance or so, they will stop receiving the messages. There are usually approaches in the messaging systems to have retries for a number of hours even. There's also some mitigation approach that are in products like ActiveMQ that is called durable subscriber and so on. So there are attempts to buffer messages for a certain amount of time, but in principle, from the pure pattern, you will not receive the messages when you're offline. And this is also solved by the same pattern that can solve the scalability problem. And we will see this in a minute. Until then, I would like to introduce a few cloud-based, cloud-native services that implement those message channels, because we will reuse them later also in the sample use cases that I have brought. So first of all, for queues, we have Amazon SQS as a serverless and cloud-native service, the simple queue service. On the right-hand side, for the publish and subscribe pattern, we have Amazon Simple Notification Service, or Amazon SNS. Again, it's a serverless and cloud-native service. And both characteristics makes the service so overly simple to use, because there's no infrastructure to manage whatsoever, and you simply use them through a very simple API. On the other hand, sometimes you are constrained to industry standard protocols like JMS or AMQP. And this particularly kicks in when you operate on-prem or you migrate your workload to the cloud. For that, you could use Amazon MQ as a managed ActiveMQ or RabbitMQ service. But this is informational. In my sample use cases, I only use serverless services. Okay, so one question that might come up also for you. What about streams? So as I said in the beginning, the focus of this talk is about messaging, but of course streams have also their uses. And there's a bit. Let's make a short excursion to streams. So there's a bit of a difference in the behavior or also in the purpose of streams and messaging. So first of all, when you deal with messaging, usually you consider each message that comes in as a unit of work. So each message for itself has a meaning and has a use. You operate on one individual message usually. It doesn't necessarily have to be the case that constantly messages come in also. Usually in messaging systems, you have additional functionality like that letter queues, and we will learn about this also in a minute. And one main characteristic is also when you receive a message from a message channel, we say you consume that message, and by consuming that message, it will also be deleted. So it will not be available afterwards. As a consumer from a message channel, you are not interested in which message is the next one that comes in because the messaging system looks after that. And the difference with stream processing is that usually the stream is considered as a unit of work or the value proposition. Usually you operate on a large amount of messages that come in from the stream. And mostly it's also a constant stream of messages that comes in. Another thing is that usually there's nothing like built-in dead letter queue functionality. And one main difference is also that messages are available after consumption until they expire. And that depends on the concrete product that you use. So that means you can also replay the messages in the stream. That can be interesting for late joiners to the party, for instance. Another thing that you need to take into account here is also that each client tracks the current position in the stream. So there's the cursor. The clients need to look after. This is kind of implied by the fact that you can replay a message. And there's another kind of integration that maybe you ask yourself, what about buses? Yeah, buses are also a form of integration approach or technology. They're quite similar to publish subscribe channels, but they are of course a bit different because they are all their own kind of product. The differences are rather blurry or so, and it's also a matter of concrete products that you look at. But most often message buses or event buses are a bit more opinionated. They usually come with integration adapters to enterprise software and so on. That makes it simple to integrate various standard software with each other. And there's usually additional features like content-based routing and so on, or pattern, schema validation or schema recognition. And because that comes with more functionality and it's more opinionated, it's also usually, it doesn't have such a high throughput as cloud-native messaging services usually have, like the ones we've seen before, SNS and SQS. They operate at massive scale, and there are not many other services that can do that. All right. And before we look into other patterns, I also wanted to introduce a bit of common vocabulary that comes in when messages are being delivered from the messaging systems to consumers. And this is visibility, timeout, in-flight messages, and message acknowledgement. So let's assume on the left-hand side, there's message A waiting in a queue, for instance. Now there is one client that receives that message out of the queue. And from that moment on, a certain visibility timeout starts. And this is expressed by the green arrow. And the purple tube now expresses how long we really consume from the entire visibility timeout. So the first consumer has received message A, and from this moment on, it becomes invisible. As you can see in the next try, there's another consumer who wants to receive that message, and it's not returning anything. And the first consumer is eventually done with it, and then they acknowledge the message or explicitly delete the message. And this has all happened before the visibility timeout has been reached. Okay, when the message is delivered to the consumer in the very beginning, and while the consumer is operating on that message, we say that message is in flight. Okay, and when it's done, we say we acknowledge that message, and during the entire time, the visibility timeout is running. And now let's see what happens if the processing of the messaging is not fast enough, so that we reach the end of the visibility timeout. So again, message A is consumed by, or is received by a consumer. The consumer operates on it. The message is still invisible, but eventually, when the visibility timeout has been reached, unfortunately, the first consumer is not yet done with message processing. That message becomes visible again for other consumers. So in this case, there's another consumer that on the right-hand side is now receiving that message. So this is something you should be aware of when you deal with messaging systems. If you want to make sure that this additional delivery does not happen, you should have a good overview of the usual processing times and adjust the visibility timeout accordingly. Okay, now let's revisit the question that we had before. How can we scale out on the consumer side when we deal with pub/sub messaging? So it's actually too simple to mention it, but the pattern is called topic queue chaining. So again, we have a publisher on the left-hand side. The publisher publishes messages into the topic. And what we can see now here is not that the consumer process is directly attached to the topic. No, there's a queue for each one in between. So as we can see in application 1, now there's nothing outstanding here yet, but we can see for application 2 already, it has launched 2 receiver processes. And now those 2 processes can share the load that comes in from the topic through the queue. And with this pattern, you have the best of both worlds, actually. So you have fan out and receiver scale out at the same time. And additionally, also you have the buffering functionality of queues. So you can also take your applications on the right-hand side offline for maintenance, and you will not lose messages. Okay, and as I promised before, let's also have a quick look at a dead letter queue. What's that in the first place? So sometimes it happens that a receiver receives a message from a queue, for instance, that the receiver tries to operate on it, and maybe there's a bug in the code, or there's a precondition that is not matched, and yeah, the consumption fails. So there's an exception that goes back to the queue. Queue will redeliver the message as soon as possible, and you don't want to have an infinite loop now going on between the two. And for that, you can set up a dead letter queue and configure it in a way that after so and so many failures on processing that message, it will land in the dead letter queue. And such messages are also called poison pills. They don't necessarily have to be malicious, but they at least cannot be processed properly. And with the dead letter queue, you can take them literally out of production, and you don't have to operate on the open heart, but then you can inspect without all the hassle in the dead letter queue what's going on. Why could this message not be consumed? And there's another characteristic that sometimes is asked for, sometimes it's asked too often for, which is Fifo queues and Fifo topics. So there are, of course, good reasons to have that, but not too many of them, if you ask me personally. But what is the reason for it? So you want to make sure Fifo first in, first out, that there's guaranteed ordering in the messages, that they come out as they go in, as we can see in this example. So we want order here. For that, there are Fifo channels, and when we reconsider the products I mentioned in the beginning, the cloud native services, SQS and SNS, they both also offer Fifo queues and Fifo topics. So if you work in an environment, now I have an application that is really that really requires the strict ordering here. Messages go out as they come in. There's something that you can think of that you can easily break it yourself. If we look at the right-hand side now, if we have more than one consumer attached to our queue, we will most likely break the ordering ourselves again, because we cannot guarantee that each message that is consumed takes the exact amount, number of microseconds on the receiver side to process. So we will most likely mess up with the ordering on ourselves on the consumer side. So how can we now make sure? Obviously, there is no global ordering possible, like from the beginning of time to the end of time or so. No, but we have to strip down the window a little bit. And if we still want to make sure that we can also scale out on the receiver side, on the overall set of messages that we have to consume, then the idea of message groups kicks in. So in this example, we have 3 message groups, the blue one that has messages A, C, and then the yellow one and the red one. And the idea behind message groups is here now, we want to make sure that every message of one message group, all messages in one message group are delivered one after the other and not in parallel. And this usually works with a concept like a group ID that you assign already from the sender side to each message. And the queue in this case here makes sure that it doesn't deliver a message from the same group as long as there is one in flight. And in this example, the topmost receiver would receive message A here, process it, and then message B can already be delivered because it's a different group. It's consumed, it's processed, all good. Now, message C would be the next one to be delivered, but message A is still in flight, so we cannot deliver this one. This is why the queue now delivers message D first. It can be consumed and processed. And eventually, message A is also processed and acknowledged. It's not in flight anymore. And now it's only a matter of concurrency, which consumer process now receives message C, and in this case, it's the bottom one. Okay, and I have 2.5 more patterns on the message routing category, and the first one is message filter, which comes in quite handy too. So as we have learned in the publish subscribe case, every subscriber receives every message, but there are often cases where subscribers only want to receive almost every message. And in this case, you could set up a number of dedicated topics, but the number of different permutations can be really large and makes it difficult to handle. Here, the message filter, sorry, the message filter pattern kicks in. And the functionality here is that each subscriber can autonomously add to their subscription a filter predicate and state that they're only interested in certain messages. In this case, the one at the bottom is only interested in purple messages. And again, the publisher doesn't have to know about it and doesn't know about it. Maybe out of interest, for Amazon SNS, there is such a filter functionality available. This operates on metadata. And as I said in the beginning, event bus services usually have a bit more functionality. Like Amazon Event Bridge is an event bus service, also serverless and cloud native. And with this one, you could have the filtering also on the actual payload of your message. And I'm also adding the recipient list pattern here just to show that certain things can be way more complicated when you don't use messaging. The recipient list pattern implements the same thing as the message filter pattern on the left-hand side, but it doesn't use messaging. It uses your own code. There's a recipient list component now that needs to know who of the subscribers is interested in what kind of message. And this can be a separate component. You can integrate it in the publisher and so on. But in every case, it means you need to have additional code that needs to be maintained, that needs to be operated. You potentially add coupling between publisher and subscriber. And that's something we don't want. So definitely a way better idea to go with messaging here. And the last message routing pattern I have brought today is the scatter gather pattern. And we will also see a concrete use case with this. Now, this is about the question how to distribute a request across potentially interested or relevant parties and capture their individual response. And this might be relevant for finding the best response or accumulate responses. And something like a request for quotes would be a typical use case for this too. And it's a composite of patterns that we already know. So we have a requester that sends out the request. It goes into a topic, and then potential responders operate on it. They work on their individual response, send it back to the response queue, where they then are sent to the last part, the aggregator that can make sense of the amount of messages that come in a way like, what's the best, what's the tiniest, what's the fanciest response. And then the requester can feedback the result afterwards. And again, also here we make use of other patterns like correlation ID and return address. Okay, with that all being said, I want to come to the concrete use cases I brought today. I brought 3 use cases. And first, I want to introduce the context for these use cases. And the context is wild rides, which is our favorite technology internet startup. And they disrupt individual passenger transportation by replacing old guard taxi cabs with unicorns, because unicorns are much more magical and much more fun than riding on a taxi cab. And their backend is based on a number of microservices. And they have shared with us what they are doing currently based on integration, and they built it all serverless. The first use case they have is submit a ride completion. So let's imagine a unicorn has just dropped off a passenger somewhere at their final destination. And now the unicorn wants to notify the Wild Rides backend about this. So it takes the Wild Rides unicorn app and pushes a button, and this leads to a request that is sent from the app. And I will use the sample use cases today also to show how you can use asynchronous REST API communications between client and backend while you use asynchronous communications under the hood. So this request goes to a submit write completion resource in our REST API. It has the expected content, and it lands in something that we call the Unicorn Management Service, which operates in the cloud. Now, what should that service do? Probably persist the incoming information, create a new resource, and then it can respond back to the client. Hey, it's all good. 201 created. I've created that resource. You're good to go. Now, you can imagine there are a number of other services in the overall Wild Rides context that are also interested about this. I have a few examples here. We have the customer notification service, customer accounting service, a loyalty service, a data lake ingestion service. Of course, everybody has a data lake today, so we have to have that. And there's the extraordinary rights service. And this is a very special one. So it's only interested in rights with a fare greater than or equal a certain amount or a distance of another amount. Now, how can we integrate the Unicorn Management Service with all the other services on the right-hand side with each other? We see already a database below the Unicorn Management Service. So we could ask ourselves, can we do an integration via database? We could just share the database with all the other services. No, we don't want to do this. Actually, if somebody in your company comes with this proposal, this is what you should answer them. Build yourself a sign with that. The bullshit stops here. But you still should do it in a polite manner. That's why the red traffic light has the shape of a heart here. Now, the thing is, when you do integration via database, you introduce such a tight coupling between all those components that I usually call lousy coupling, because it's so lousy that if you change anything in the database schema on the one service, then you will break the integration with all the other systems. And there's so much coupling involved here that let me land a joke from Roy Fielding that I have read about him, that I have read from him. There's so much coupling involved here that this architecture should be X-rated. So let's not do that. But what about integration via REST APIs? Oh, we just spoke about Roy Fielding. REST APIs are a great thing. They are based on the architecture of the web, and the web is obviously a largely loosely coupled system. And absolutely, we can do that, but it comes at a cost in this scenario. So we would have to know, first of all, we would have to send HTTPS requests to all those systems, and we had to know what are the addresses. So we are back to the recipient list pattern, or maybe to the recipient list service pattern even. So we said before, we don't want to do this. Also, the filtering here for the extraordinary write service, we would have to implement this on our own. Again, additional codes that we need to maintain, manage, and operate. We don't want to do that. Now comes a decisive question: integration via messaging, maybe. And as you could guess, absolutely. That's the way I would propose to do it. So you could simply add a topic here. Let's call it the write completion topic, and we are using Amazon SNS for that. It's a unicorn management service, can simply send a message into that topic, and all the other service on the right-hand side can subscribe to the topic individually. The unicorn management service doesn't have to know or do anything about it. Also, we can use the SNS message filtering. And again, we don't need to implement something. It's just a configuration aspect that the extraordinary write service needs to look after. And if we also want to make sure that all messages are being buffered, so you can take down your other services for maintenance, or if you want to flatten peak loads, then we can add queues in between, and we are all good to go. The data lake ingestion service is a service that we are going to revisit in one of the upcoming use cases once more, and also consider if we shouldn't maybe take a look at streaming for this case, just as a heads up. Now let's look at another use case. It's called the pre-booking campaigns. And what WildWrites is doing here is they run massive campaigns with a call to action: book this week. So imagine they have pop-ups in your browser, they have commercials in live TV or in streaming shows and so on, where the audience is asked, if you want to get a good discount on your ride for next week, book it already this week. And now it's the WildWrites customer who takes their app and pushes the respective button. That leads to a request against the submit write pre-booking resource, and it comes with the necessary details. Now it ends in the write booking service. And to make it more explicit, I didn't have space for it in the previous architecture diagram, but to make it more explicit, I explicitly put here a managed API gateway component, because usually that's also something you would do. You wouldn't want to do the API management in your service itself, but you would want to place an API management gateway in front of it. So that's all the scope of the write booking service here. And what does the write booking service do? It apparently wants to persist also this incoming pre-booking request. All good. And then it can respond to the client to a one created. So we took good care of your request. You're good to go. Now, WildWrites do a massive campaign with another CTA. Book today. So not book this week, but book today. And now they expect that the load will be dramatically more than before. And they are looking for a way to further decouple the processing, even within that service, within the write booking service, to make sure that they can always handle everything. And the idea behind it is that the most important thing also from a customer experience is that the pre-booking requests are being accepted. The actual processing can happen a few seconds later or so. That's not a problem, but the pre-booking request as such needs to be accepted. So we split it up here in a little bit, and we only have a pre-booking pre-processing resource here that just accepts the incoming request, does a little pre-checks, sanity checks, and so on, and then hands it over into a topic, and then responds to the client. 202 accepted this time. So because it's not completely processed, but we are still working on the backend. And that's why the response to the client is now accepted, and the payload is then a task and status representation, which the client can also use to update the status eventually. Now, in the further course, there is a pre-booking processing resource that takes care of it on its individual pace. And it is also fed through a queue to make sure that no message is lost here. So with that, we have a decoupling of different steps within the same system even. And just to express that, there are usually other services who might also be interested in the pre-booking information. I have put the data lake ingestion service once more with the data lake ingestion processing resource. And as I I will, as I have announced, I will speak about the data lake ingestion service also within this use case in a bit. But first of all, there's an even more aggressive campaign going on now. Now imagine during a primetime TV show or streaming show, the CTA is now book now. Dear customer, book your ride for next week in this very moment. That means from 1 second to the other, you might have a load of from 0 to several tens of thousands of messages coming in per second. So what's the first thing you could think about? Just put a queue in front of your pre-booking processing resource. So in this case, we have an SQS queue put in front of it instead of the API gateway. And this is something that you can do when you own the code of that one branded client that you have. Then you could also set your client up for communicating with the SQS API directly. On the other hand, if you want to open your API to third parties or even long tail developers, then you would again want to have an API gateway in front of it and just expose your regular REST API. But with this, you can make sure that even that immense loads that comes from such a CTA as book now, you can handle that load. And as I said, the data lake ingestion service. So one could correctly argue, do we really have to have that ingestion processing resource at all? Maybe if you have some esoteric pre-processing in place or so, but usually you don't really have to. So what you have in streaming, usually there are tools that can directly offload huge batches of messages into a sink. And here I have instead now simply connected my modern data platform, which has a data lake in its heart. And through that ingestion stream here, now simply all the messages that go into the pre-booking forwarding topic are then offloaded into the data lake raw data tier. And this is based on Amazon S3 as a cloud-based serverless storage. Okay, we have a few minutes left, and I have one quick use case also left, the instant write RFQ. So as Wild Rides is a very progressive company, they thought about this use case where the customers don't just book the next available unicorn from around the corner, but they want to run an RFQ, a request for quote, with the unicorns in vicinity, and then just take the offer that is best for them. And that can be the one with the cheapest price, or maybe with free drinks during the ride. How does that look like? So the customer sends out the RFQ request using the app again with the necessary data. It lands in the right booking service. And now we apply the getter gather pattern for this. So those, first of all, yes, we need to answer the client, of course. And again, since such a request, such an RFQ takes a few minutes, let's say 5 minutes by default, we directly answer to the client to accept it. Hey, we have accepted your input. We are working on it. And here's a link where you can also check for the status. And there's also an ETA because there's a default of 5 minutes. Now, this RFQ request is forwarded into a topic, and all unicorns in vicinity that listen to this topic now can work on their individual response. Maybe they are not interested, but if they're interested, they can work on their response and submit their response back into the RFQ response queue. And from there, the ride booking service aggregates the results and provides a list of all those quotes that came in from the unicorn back to the customer, so that the customer can choose the best one. But as long as this is running, what can the customer do? So they can use the link from the previous response to retrieve the RFQ status. And as long as it is running, they will still see status running. The ETA probably remains untouched. And again, the link to refresh. Eventually, time is up, and then the status is done. Now there's a link to retrieve the result available. And when the client sends a request to it, they will get back then the individual quotes from all those unicorns. And that was this use case. Before I let you go or open it up for question and answer, I have a few resources to share with you and also a call to action. So first of all, there's a blog series where we also talk about all these use cases and patterns. If you want to read this all once more for yourself, and there's even a bit more content in there, you can do that. If you want to listen to this entire thing once more, there's also a recording from reInvent where I talk about this and have even one more use case. And if you want to get hands-on with all this, there's actually also workshops that implement a few patterns that I showed today. And we actually deliver this workshop also on Friday here within the JCon scope. So if you fancy getting your hands dirty, just join us there. One thing I want you to remember from today is that loose coupling is always better than lousy coupling. And with that, thanks a lot for listening today. Please also feel free to reach out to me on Twitter. You see my handle here. And apologies once more for the coughing all the time. I don't know why this happened. Okay, and with that, I'm done. If you have any questions, I'm here.